All right, so it's the time we've all been waiting for, stoichiometry. And so we're going to go through some of the first examples of working stoichiometry problems. So grab the popcorn. Here we go. So here's a prototypical chemical reaction. Ammonia can react with nitrogen monoxide to form nitrogen gas and water. And we have a balanced chemical equation here, so there are the coefficients. And as you'll hear in class, hopefully before you see this video, the coefficients in front of each compound, each of the reactants, each of the products, are conveying the mole ratios between the various compounds involved. So for example, we know that if we put in 4 moles of ammonia and plenty of nitrogen monoxide, then we're going to get not 4 moles of water, but 6 moles of water. That's just the way the stoichiometry of the chemical reaction works. So, and we can use those mole ratios to make very nice predictions as to how much product we're going to make given a certain amount of starting material. So, for the first question, the question is asking how many moles of nitrogen gas, this stuff, can we produce if we start with 1.5 moles of ammonia and we have an excess of nitrogen monoxide. Okay, so I'm going to put this is something we'll do in class. Let me do that a little bit neater. It's kind of like saying, hey, we want to make cheeseburgers. I'm going to give you more than enough hamburgers, but I'm only going to give you a certain amount of cheese, okay? So you will definitely run out of the cheese before you run out of the hamburgers. If I give you X numbers of slices of cheese, how many cheeseburgers could we make? So it's kind of that analogy, all right? So we don't have to worry about running out of nitrogen monoxide. What a relief. But we are being told that we're going to be given 1.5 moles of ammonia. Okay, so how much nitrogen gas could we get out of that situation? All right, so what I like to do is start by writing down the thing that we're trying to calculate, right? And that is moles of nitrogen gas. So I just start by saying, moles of nitrogen equals. Okay, so that kind of gets me set up. I've done this many, many times in other calculations, whether they be unit conversions or mass to moles conversions. It's just kind of a nice anchor here. You can always kind of look to the left and remind yourself, oh, this is what I'm calculating. This is what I'm trying to get. And then what we're given is 1.5 moles, so we write down that amount, 1.5 moles of ammonia. Ammonia is NH3. And then there comes the conversion factor, and this is where we place the mole ratio as given by the balanced chemical equation. All right, so before we kind of get into the mechanics of the calculation, I think it's really important, don't lose sight of the forest for the trees here. Let's just sit back for a second, get comfortable, and think about what you're being asked for. All right, you are being asked to determine how many moles of this stuff, nitrogen, could be made if you were given 1.5 moles of this stuff, right? So if you're given 1.5 moles of this, how many moles of that could you get? Okay, so if you look at the coefficients on these two compounds, you know that if you start with 4 moles of ammonia, you're going to get 5 moles of nitrogen out, right? So you can rest assured that for any quantity of ammonia that you start with in this reaction, you should end up with more than that number of moles of nitrogen. So then in this specific example, if you're given 1.5 moles of ammonia, do you think you're going to end up with more than 1.5 moles of nitrogen gas, or do you think you'll end up with less? If you said more, you're right, because again, look at, compare the coefficients on the two compounds that are being talked about here, and you can see that for every mole of ammonia that goes in, you're going to get more than a mole of nitrogen out. Okay, so this mole ratio should be it should amount to a fraction that's greater than 1. Okay, because I think you can see where this is going. We're going to end up with more than 1.5 moles of ammonia. Okay, so I don't mean to belabor that point, but I want you to kind of keep your wits about you and sort of see the bigger picture as you're plugging numbers in, okay, because that's going to be a very important error checking mechanism for you. All right, so because we're trying to calculate moles of nitrogen, what we're going to do is put the coefficient for nitrogen in the numerator, okay, and we're going to put the coefficient for ammonia in the denominator, because that's what we want to cancel those things out, right? We want to be left with moles of nitrogen. Okay, so when we go through when you do the math, what you'll find is that you should get 1.9 moles of nitrogen gas. It's a diatomic. On your calculator, you'll probably get something like 1.875, but notice we're being given two significant figures in the information, and so we should use two significant figures in our answer. Okay, so there you go. And let's see here. Yeah, I think that takes care. That's that. All right, let's go to the next problem. Let's see here. Same chemical equation. All right. This time the question is asking something a little different. So again, it's saying assume that we have an excess of where's my pen? An excess of nitrogen monoxide. Okay, so excess. Again, that means you don't have to worry about being limited by this amount. And it says how many moles of ammonia would be required to produce 15 moles of water. Okay, so again, we're being asked for we're being told we want to generate a certain amount of a product of the reaction. How many moles of one of our reactants are we going to need? Okay, so just like last time, we're being asked for the moles of ammonia, so I put moles of ammonia equals, and then we're given 15 moles of water, so that's 15 moles of water. And now let's stand back one more time. Let's do a reality check. You can see that the mole ratio. Oops, I forgot I had a little animation in here. The mole ratio between ammonia and water is 4 to 6. Okay, so what that means is if you put in 4 moles of ammonia, you're going to get out 6 moles of water. In other words, you'll get 1.5 times as much water as you put in ammonia on a mole basis. So if you're wanting to generate 15 moles of water, okay, it's kind of a converse situation. If you want 6 moles of water, you're only going to need to put in 4. So if you want 15 moles of water, you'll probably end up putting in something less than 15 moles. Okay, so let's see how that pans out. So let me restate this again. Moles of ammonia equals 15 moles moles of water, and we're going to multiply by our mole ratio. Since we're trying to get ammonia, we put the the coefficient for ammonia, 4 moles of ammonia up there, 6 moles of water in the denominator. Okay, and notice it's very consistent. The thing that we're trying to find out for our answer is what's going to be on top in the numerator. All right, and we're trying to cancel out water, moles of water, so that those have to be in the denominator. And when we multiply through, I think you can see that 4/6, that reduces to 2/3, and 2/3 of 15 is 10, right? 10 moles of ammonia. Okay, so it's really just that simple. If you're kind of following, if you're kind of getting a feel for what we're doing here, you, my friend, you're in the stoichiometry zone. You're doing fine. Okay, 10 moles of ammonia. And I'll tell you what, I'm going to stop the video here. There is one more problem that I'd like to demonstrate, and I'll do that on the next video. Okay.